In this lecture, I want to look at what I'm going to call a networking problem. This is a pretty standard problem in graph theory, although it doesn't have a colorful name like the traveling salesman problem. Here's the statement of the problem. Given a weighted connected graph, find the spanning tree of least weight. Now, if you think about the words here, you should see that we've studied everything except spanning tree. We don't know what that means. So first we'll learn what this phrase means, spanning tree. Well, let me remind you, a tree is a connected graph that has no circuits. Here are 3 examples that we saw earlier, and you could draw for yourself many other examples. Now, suppose you have a connected graph. And suppose that you choose some of its edges in such a way that the graph you get is a tree. Now, what I mean by the graph that you get is the graph that you get by taking all of the vertices in the given graph together with the edges you've chosen, and you ignore or throw away all the other ones, the ones you haven't chosen. So if when you do that you get a tree, then this tree is called a spanning tree. And you're looking at an example. If you consider that graph on the right and ignore the way that I've colored the edges for the moment, you'll see that we have the complete graph on 6 vertices. Now, the reason I've colored some red is those are the ones that I want to choose. In fact, I've chosen 5 edges over there. And if I now look just at those edges and I look at the vertices and I ignore the ones that are in black, you'll see that I have a tree. That is to say I have a connected graph with no circuits. Now that may not be immediately obvious because you'll see that those edges are crossing over each other, but we know that's meaningless, and we know that we could rearrange the vertices in such a way that those 6 edges would not be crossing. Notice, by the way, that I chose 5 edges, and of course I have to because we know that if you want to have a tree with 6 vertices, then you need 5 edges. So in this graph, if I'm looking for spanning trees, I know that I need to pick 5 edges. They can't be any 5 edges because, well, I want to avoid having circuits and I want to have something connected. But if I'm going to have a tree, certainly I will need to choose some 5 edges. Let's look at this example. So over on the right, I'm giving you a graph. It's certainly not a complete graph. It's very far from a complete graph. And I'd like to figure out how many spanning trees there are in this graph. Now, I could actually draw them all systematically, but what I'm asking us to do simply is to think about how many there are. In other words, to count them. Now, first of all, let's ask ourselves how many vertices there are. Well, there are 7 vertices. Also, there are 8 edges, so of course it's not a tree. 7 vertices and 8 edges. If we wanted to have a tree, we would need 6 edges. Now, we're not just allowed to draw edges anywhere we want them. The edges that we're supposed to be using for the tree should be among the edges that are already available. So we need to take 6 of those 8 and get a tree. To say it another way, it may seem simpler to think about it this other way. We have 8 edges. We want 6. That means we need to erase 2. So if you're trying to figure out how many spanning trees there are here, you need to ask yourself, how many ways can I erase 2 of those edges so that what I have left is a tree? Well, there are some edges that you can't erase at all. So consider, for example, this edge. You can't erase that. You can't throw that one away because that will disconnect the graph. And the same thing applies to the one at top right. On the other hand, here we see a circuit. And we don't want to have a circuit, so we realize that we need to erase one of those 3 edges. And in fact, the same thing over here on the right. Here is a circuit, and we want to erase one of those 3. So we need to erase one on the right, one on the left. There's no overlapping here, so in fact, you can make any choice freely on one side and any choice freely on the right side. There are three possible edges on the left. You must choose one to erase, and over on the right you must choose one of those three. So, by the fundamental principle of counting, the number of spanning trees is 3 times 3. Now, if you'd really like to reinforce your understanding of what I just said, a good exercise would be to draw all of those spanning trees, to make 9 separate drawings. Now, here we have a complete graph. And a complete graph has lots of spanning trees. In fact, the one shown over on the right, this complete graph with 6 vertices, has 1,296 spanning trees. In general, we have this wonderful simple formula for the number of spanning trees in a complete graph. If the complete graph has n vertices, then the number of spanning trees is n raised to the power n minus 2. So, for example, in the one that we're looking at, n is equal to 6. And so the number of spanning trees is 6 to the 4th, which is indeed, as I've said, 1,296. Now be careful, this formula only applies to complete graphs. Don't try to apply it to other kinds of graphs. But for a complete graph with n vertices, the number of spanning trees is n to the n minus 2. Now, back to the networking problem. If you begin with a weighted connected graph, then each possible spanning tree has a weight. I think that's sort of obvious what that would mean. Namely, add the weights of all the chosen edges. That's a number. That's called the weight of the spanning tree. So now we understand completely the statement of the networking problem. We are given a weighted connected graph, and we're asked to find the spanning tree of least weight. Here's an example. Again, we're looking at the Ohio State campuses. We're looking at edges in which the weights represent the distances. Now, we're not going to do the traveling salesman problem this time. What we're going to do is, suppose we want to make secure internet connections. And suppose that each connection between a pair of campuses is proportional to the distance, let's say $1,000 per mile, which will make you think maybe it's worth thinking about this problem. Now, there's no point in having circuits. You see, what you want is you want a spanning tree. You want people in every campus to be able to communicate with people in every other campus, but you don't care whether those communications are routed through another campus. So, for example, we don't necessarily have to have that edge, which would look rather expensive, between Lima and Newark, if they could communicate by sending messages via some of the other campuses, right? Lima to Marion to Columbus to Newark would be perfectly okay. These messages travel at the speed of light, so nobody really cares that they have to go that extra distance. So there's no point in having circuits. What you want is a spanning tree. Now, of course, you'd like to have the cheapest one, and so, sure enough, you're trying to solve this networking problem. You're trying to find the spanning tree of least total weight. Now, let's think about one possibility. The administrators in Columbus will naturally think to use what I'm showing you here. Namely, they'll think, well, let's choose the 4 edges coming out from Columbus. Okay? And then if you do that and add up the weights of those 4 edges, which is 50 plus 96 plus 67 plus 40, you'll get a total weight of 253. Now, if we're thinking that's the cost in thousands of dollars, that's $250,000. So it's certainly good to ask, is that the best we can do? In other words, is this the spanning tree of least total weight? What we seem to need is an algorithm for solving that problem, and that's what we'll be looking at in the next lecture.